In this video, we're going to look at the different components and parts of circles. We'll have a look at their terminology and also how we go about calculating them. This one is to do with angles in degrees, and there'll be a follow-up video which will talk about how you do it when you're measuring your angles in radians, which means that the formulae are slightly different. So this one's angles in degrees. Okay, so a little bit of terminology to start with. We already know radius, clearly. So we've got radius of a circle. What we're talking about now is, or starting to talk about, things like arc length. So this L here is arc length. Okay, and that's measured as the proportion, the part of the circumference subtended by this angle. So we talk about things being subtended by angles. So that's the sort of the angle between. So we've got arc length there. We also talk about sectors. So a sector is this bit, the shaded green bit in here, so that obviously is going to be a proportion of the area of the total circle as defined by that angle theta. Over here we have a straight line between 2 points on the circumference, and that's called a chord. Okay, and you can see that it slices off this bit here, sort of curvy shaped part, but also a triangle over here, and it's subtended by this angle. So that's the chord, it's the straight line. The shaded bit here is called a segment. So it kind of looks like the segment of an orange, if that helps you remember the difference between segment and sector. So the segment is the bit that you get left with after you draw a chord, and that splits your sector, because OED around the side is your full sector. So you can split that up with a chord into a triangle over here, and then the segment over this side. Now we do just have to be a little bit careful with major versus minor arc lengths, sectors and segments. Okay, so in any case, unless your angle in the middle here is 180 degrees, then one side is going to be bigger than the other. So over here we've got the minor arc length, which runs from B, that's a bit big, here, from B round to C, that's your minor arc. Okay, your major arc is round the other side. So they're calculated in the same way, as we'll see a little bit later, the only difference being the angle that you use. So obviously for the minor arc you use this angle in here, okay, and for the major arc you use the reflex angle around the outside. Call that phi. Okay, the same deal, you have minor sector in here and a major sector on the outside. So if you're given a question, you're given a circle and it says find the major sector, but it gives you this angle theta, then you just have to pay attention and make sure that you get the reflex angle on the other side. Same thing over here with segments. We've got a minor segment in here, which is the bit that looks like part of an orange, cut off by the chord, and then the major segment is whatever's left. Okay, so usually we find ourselves talking about the minor segments, but just be aware that it might ask you for the major segment. Okay, so let's have a look at some examples here. So we want to find the length of minor arc AB. Okay, so AB, we're looking at this length in here, from there to there. Okay, now we've got a nice angle of 45 here. We know that 45, if you split a circle into 45, that's 1/8. So 45 degrees is 1/8 of a circle. Okay, so what I can look at and say, well, I know how to work out the circumference. Okay, the circumference is just 2 pi r. Alright, and if I want to work out what is 1/8 of that, then I can just work out my arc length as 1/8 of 2 pi r. So 2 times pi, in this case, radius is 12. Okay, and you can either leave that, so you can cancel this out and make that 4, and then you've got 12 and 4 is 3. So you can leave that as 3 pi, or you can work it out to 2 decimal places and have it as 9.42. Either way. Okay, so that's our arc length. Alright, just a proportion of the total circumference. And you can do this with any angle. So if we're going to generalize, we can say that the arc length is just theta divided by 360, because that gives you the proportion of the circle that you're dealing with, times by 2 pi r, which is your circumference. Okay, so we're just talking about proportion of the circumference. So that's your circumference, and that's the proportion there. So that's your formula for arc length, and that'll work for any angle. Okay, now we're looking at sector, so we're going to do the same thing. So we want the area, and we're talking about the minor sector. So minor sector is, of course, this bit in here, this piece of pie. Okay, and we can do the same thing. We know it's 1/8, so the area is going to be 1/8 times, and of course the area of the circle is pi times r squared. 1/8 times pi times 12 squared. Okay, and if you work that out, you get 56.5, or you can work it out and leave it exact in terms of pi, if you wish. Okay, so we've just done the same thing. Worked out the area of the circle and divided by 8 because we know this proportion is 8. So again, to generalize, the area of the sector is just theta divided by 360, gives you a proportion, multiplied by the area, the total area of the circle. So total area. Okay, and of course, remembering that theta is in degrees here. Oops, degrees, because we're dividing by 360 degrees there. Okay, now the chord length, so the chord length is a straight line between A and B. Remember, the arc length is the curvy bit, but the chord length is the straight line. Alright, we want to find the chord length of that. So if we forget about the fact that it's actually in a circle, and let's just look at it's a triangle, okay? CA is the radius, that's 12. Well, CB is the radius as well, so that must also be 12. Okay, and now I've got a triangle where I have two sides, the included angle, and I want to find the third side. So that should be yelling at you, cos rule, okay, because we can use that to find the third side there. So we're going to find x, so we can say x squared equals, now because these are the same, we've got 2 times 12 squared, take 2 and again times 12 squared, because this is in your rule it's a squared plus b squared, take 2 ab, okay, and then cos 45, and if you work that out, you should end up with 9.18 centimeters as x. Okay, so just using the cos rule in order to find the length of the chord. And to generalize that, because of the nature of the radius being the same, so those two sides of the triangle are the same, you can actually simplify it. And there's a couple of ways you can do it. This way is using the cos rule. So that's saying 2r squared take 2r squared cos theta. So you can factorize out the 2r squared, and that just gives you 2r squared outside 1 minus cos theta. Remembering, of course, that this is pq squared. So the chord length is pq squared. So in order to get pq, you need to take the square root of that. So don't forget that bit. 1 minus cos theta. Okay, or we can look at it this way. If you split this into two triangles, this is a right angle triangle here, and we say, well, let's just look at AQ. Using our SOHCAHTOA, we know that AQ is r sine theta on 2, where this is theta on 2, where the whole angle's theta. Okay, therefore PQ from here to here must be twice that. So PQ is 2 times AQ. Okay, so that's where you get your 2r sine theta on 2. So you can use either one of those. It's up to you, whatever makes more sense to you or whatever you feel like using at the time, but you can use either one. Okay, so let's have a look at an example that kind of does a bit of everything. First thing we want is the length of the minor arc AB. Okay, so remember to read that. So minor is over here, AB subtended by 100. So the arc length is going to be 100 on 360 times 2 pi, and the radius is 3. Okay, and if we work that out, you should get 5.24. Alright, so that's your minor arc. For your, so that's 1. For your major arc, or sorry, major sector, okay, so now we're talking about this angle around the outside, which of course is going to be 260. Okay, so the area of the major sector will be 260 on 360 times pi times r squared. Alright, this is something that's always likely to trip you up in a test or an exam, is you're rushing through and you're like, oh yes, I know how to do this, but forget to use the correct angle, so just make sure that you check that. Okay, and if you work that out, you get 20.42. And of course, we don't have units on here, so we're just going to call it units, and units squared for area. Alright, 3. The length of the chord AB. So I'm going to use the cos rule derivation. So that's your 2 times r squared times 1 minus cos of the angle. I'm taking the square root there. It gives you 4.6 units. Okay, now the last thing, the area of triangle OAB. So we want this triangle. Okay, again we know that 0A is the radius of 3, 0B must also be the radius of 3. Now I have a triangle where I've got 2 sides and the included angle. I can use my sine rule for area of a triangle, which is my half AB sine C. Okay, so A and B are the same, so half times 3 squared times sine of 100. And that will give me 4.43 units squared. Okay, so all these things we can find out with just knowing the radius and the subtended angle in there. Alright, so let's look at segment area for the same one. So the segment area is this here. Now we worked out, well we actually worked out the major sector. We need the minor sector obviously because this is, we're going to find the minor sector. Okay, and what we want to do is say, well, the segment area is going to be the minor sector minus that triangle which we just worked out. Okay, so the minor sector there will be 100 on 360 times pi times 3 squared. And then we're just subtracting what we had before, which is 4.43 from the previous slide. Okay, and calculating that gives me 3.42 units squared. Okay, so in order to get a generalization for segment area, we have the area of the segment is the area of the sector, given by this, minus the area of the triangle, given by that. Okay, so if we work that out, we get theta on 360 pi r squared minus a half r squared theta. Okay, and if you wish, we can factorize that out. Sorry, ooh, hang on. Sorry, wait a minute. We've got, that's the sector. Sorry. Hold on just a second. Confusing myself there. Right, the area of the triangle is a half r squared sine theta. So it's very similar to this in radians. That's in radians. We're using this one. Okay, yeah, and if you like, you can factorize out the r squared. It doesn't really help you all that much. We take r squared out of there, and you get theta pi on 360. Take sine theta on 2. Okay, so that's your segment area. It's probably easier just to remember this and work them out separately, rather than trying to remember that formula there. Okay, but just be careful. Consistency in units is really important. So that's the old radians versus degrees argument, knowing what you're working in. Okay, so we were using this one here. Okay, so in summary, when theta is measured in degrees, okay, just highlight that, measured in degrees, these are your formulas that you need to remember. So arc length, just theta on, well, they've actually simplified it here. They said theta on 180 times pi r. I tend to remember it as theta on 360 times 2 pi r, but whatever works for you. Okay, the chord length, so they've used the 2r sine theta on 2, or you've got the one that you can use for the cos rule. Area of sector is theta on 360 pi r squared, just your proportion of area, and then your area of the segment is your area of the sector minus the triangle. Area of sector minus triangle. And just remember to check, is it major or minor that they're asking for?